So the title of my talk is Advancements. Am I audible?
Yes, sir, you are audible.
Okay. So the title of my talk is Advancements in FRP Composites for Structural Applications. In fact, a lot of people have worked here as well. Our civil department, mechanical department, metallurgy department are working on composite material. It's in from our department itself. So a couple of faculty also working in composite material, but still I thought let me introduce and finish. So an engineered combination of materials that result in a finished material with better overall properties than the starting constituents. So at a microscopic level, the constituent materials remain distinct with the finished structure. This is one of the greatest inventions of 20th century. These are some of the applications of the composite materials. Actually, in fact, from the Stone Age, tools and weapons are there. So then wood and bamboo are available as natural composites. Then metal, then comes the age of metals. Then comes polymers, ceramics and composites. So initially the straw reinforced bamboo bricks, iron for reinforcement of masonry, reinforced cement concrete. These are the composite materials being used at the history. If we talk about the history of composites, then comes the fiberglass boat in 1942. Then aircraft applications, more or less similar to that time. Missile applications, boron and carbon fibers, advanced composite in aircraft, Kevlar fibers. So basically 1980 to 2020, there are significant applications in many areas. So further the development has occurred. Nano composites, fiber metal laminates, functional graded material. These are also developments of the composite material. You might have recent news, you might have seen in the news. So the Israel has sent a 100 aircraft of F-35, F-35, including F-35, F-16 was also there, F-35 was there. So these are the sophisticated aircraft, which are many of the components are made of composites. That way it is. I will show you there are a lot of applications to that one. So FRP composites are manufactured for a polymer matrix and a reinforcing fiber. So the fibers can be glass fiber, carbon fiber, aramid fiber, hybrid fiber means combinations of above fibers, Kevlar fibers, natural fibers like jute, flax, cotton. These are natural fibers. Similarly, polymer material is epoxy, polyester, polyurethane, polyethylene, and then comes the development nano composites. Carbon nanotubes are used also in preparation of the composites, aluminum powders, graphene. These are some of the development of new composites, which is called nano composites. As I have told you, there is a lot of applications in aerospace, automobile, nuclear sector, marine sector, civil engineering, sports goods, and many. Every day you must be seeing cricket bat. So the costliest bat is made of composites only. So starting from the normal wooden bats to which we practice during school to current recent cricket bats, table tennis bats, rackets, and many. So all these aircraft, so these are bigger applications. So civil engineering also glass fiber roofs. So a lot of applications are there. There are some figures also I will show you. Basically, it has it is it has strength and it is lightweight as well. So we have materials which are available of high strength, which but weight is heavy. We were having materials which are light like aluminum versus steel. Steel is quite strength is high but heavy. Aluminum is light but it's not that much strength. So basically there is a term like specific strength and specific stiffness. Means actually specific strength means strength per unit weight. The strength per unit weight is for this composite material is high. So strength, that is the specific strength and specific stiffness. Besides that, there is low density, high corrosion resistance, longer durability, high internal damping, low maintenance cost. These are some of the reasons of the applications of composite. The tensile strength of composites is 4 to 6 times greater than of steel and aluminum. The strength to weight ratio of FRP is 18 times that of steel and 50 times that of concrete. That's the level of applications advantage of in terms of the strength to weight ratio. FRP materials that are 30 to 40% lighter than aluminum structure. The composite bridge in Oxford, the Aventine passenger car. If the new cars are coming with composite material. Canoe trucks, the award-winning Oracle sailboat are some applications of the FRP composites. Besides this, military aircrafts like F-35, which recently being used by Israel to Iran. Even the recent Boeing 787, the passenger plane, Airbus 350, 380 passenger planes uses more than 50% of composite. So Boeing 777 uses only 12% of composite, while Boeing 787 uses 50% of composite. So that's the development of the advancement or development of technology due to that one. The F-35 Lightning II, which was used by Israel in Iran, will be the first mass-produced aircraft to integrate structural nanocomposites in non-load bearing airframe components. Meanwhile, same carbon nanotube reinforced polymer material is being considered to replace about 100 components made with other composites or metals throughout the F-35 airframe. So many nanocomposites are being used, especially CNT, carbon nanotube. So in F-35, these are some of the photos. So this is the Aventine car. This is the roof. MIT campus, the composite wood canoe truck. This is the Singapore airport building, main building, departure building. So all are made of mostly composites. So this is the Boeing 787 Dreamliner. We have around 50. So this is the this is the what are the uses of, as you can see, composites being used by 50%, steel used 10%, titanium used 15%, aluminum used 20%. So by comparison, the 777 uses 12% composites and 50% aluminum, whereas 787 uses 50% composite. That's due to Airbus 350, Airbus 380, full composite wing and fuselage panel. Fuselage is the main body panel, is called fuselage. So these are the wings and this is the fuselage panels. So these are made of carbon fiber reinforced polymer plastics. So this is the Oracle sailboat, with the winner of the 33rd America's Cup. This is the micro air vehicle, small, so which weighing 3 grams, measuring 10 centimeter, are being manufactured and used for different kinds of purposes. So it is a remote control aircraft with camera and image recognition software. Drones, these are used as drones. 9 Ukrainian nationals detained in Tamil Nadu for using this drone to take photos of the Tirumalai temple. Drones fly at altitude of 50,000 feet and can monitor the movement of objects as small as football. Now you can see the lot of uses are done by the drones in defense sector, in also normal trades, cultivation, everywhere it is being used. Business purpose also, flood control. This is the Israel drone, which we have procured from Israel, and he is naturally using at other places. This is the F-35 Lightning II fighter jet, which made up of nano composites. So this is what is called fiber metal laminate. This is initially composite were being used. So then people thought of using one layer of composite and one layer of material metal like aluminum. So one layer composite, one layer metal. So this is called fiber metal laminate. So if it is aramid epoxy is the composite, then it is called aral. If it is glass fiber epoxy, it is called glar. If it is carbon fiber epoxy, then it is called caral. So these are along with aluminum, this is used. So this is the development. This is the improvement of technology due to what we are using in 1950, the commercial car, and today's commercial car. So the low weight. Low weight means everything is your fuel consumption becomes less. Naturally, your speed is depend upon that one, depend upon the weight. There is significant utilization on unique design models as well. So this is the commercial car bodies. So the back side of the car bodies, body panels, valve covers, truck belts. You can see the usually this is the failure occurs here, but now whatever you call it, fiber plastics. So those are only composites. So these are the recent developments in the design freedom is there. Heavy truck 1960s, so first use of heavy truck. Now 90% of heavy trucks are composite body. So due to low weight, corrosion resistance and durability. This is the windmill of 1980, and this is the wooden wind turbines of the today, which is previously it was 15-meter diameter, now it is 150-meter diameter, and which was capacity 50 kilowatt, now it is 7.5 megawatt capacity. So it is due to the high strength, toughness, low weight, corrosion resistance, due to that only. And this we have already know. 1970 the Concorde was 8% composites. Now Boeing 787 is 50% is composites by weight, 80% by volume. This is the F-19 Lightning II, F-35. From you might have heard of American fighter plane F-16, F-18, then comes F-35 Lightning II is the latest one. So these are some of the advances in design of composite materials. So initially there was static analysis. In fact, I saw when I come to the NIT, so I saw a lot of metallurgy people are doing static testing of composite material. So we started in our laboratory vibration testing and stability testing of the composite plates and cells. Then we have done it here. Most of the things have been done it here. Not only it is a development of composite materials, and in fact we have practiced also here. Many students has worked on one worked on vibration, one worked on delamination, one worked on composite subject. Delamination means actually, so let me tell you, so composite material is nearly 2 mm, 3 mm like this one. Multiple layers are there. So multiple layers with epoxy and fiber, epoxy and fiber, epoxy and fiber. These are multiple layers. So sometimes from layer to layer, so it get detached. That's called delamination in composite panels. That's called delamination in composite panels. So we have casted some specimen without delamination, with delamination, different degree of delamination, and try to find out the stiffness, try to find out the natural frequency, because dynamics is our main concern. So for plates and cells, we have done it also. Composite subjected to hygrothermal loading. So this also comes to our mind when I have traveling in a plane. So I saw that the pilot is announcing the temperature of the space is minus 50 degree, minus 40 degree, minus 60 degree, around that one. So it comes to our mind, if composites must be sustaining, so we try to cast some specimen with in summer we experience plus 50 degree, and in space when it goes to the air it is minus 50 degree. So the composite has to sustain in both the situation. So hygrothermal means temperature and moisture, temperature and moisture. So different treatments have been done to the composites, and we find out the uh, dynamics of those kind of components. FRP composite cells, we have done it like actually told you. Initially, we worked in plates, then we have extended to cells as well. Then fiber metal laminates. So fiber, glass fiber, and aluminum in alternate layer. We have done also. One student has done it, the fiber metal laminates. He has done the dynamics as well as fatigue behavior of fiber metal laminates. Actually, fatigue behavior is a significant behavior which usually of practical significance to the aircraft structures. Then another one student has worked in stiffened composite plates with stiffeners in horizontal direction, vertical directions. I will show you. So the different specimens will do that. So then fatigue behavior of composite plates, as I have told you. Then composite beam with cracks. So the dynamics of composite beam with cracks. Then we have worked in, right now also the work is going on. Let's see to complete nano composites. So composites with carbon nanotube, composites with nano alumina, we have done it. Composite with graphene, we are yet to try. The importance of dynamic analysis, static analysis when loads are slowly applied. The loads when loads are suddenly applied or variable in nature. Most of the loads are dynamic except self load. Live load is changing, wind load is changing, and earthquake is perfectly different. So the mass and acceleration effects comes into consideration. So dynamics is everywhere except the self load. If a structure deformed elastically and it is called, it vibrates about its equilibrium position. The periodic motion due to the static strain energy is called free vibration, and the number of cycles per second is called the frequency. The maximum displacement from the equilibrium position is called amplitude. In practical situations, vibrations subside with the time due to damping. So this is a Tacoma bridge which is failed due to the vibration and repaired also. This is how a composite looks like. So fibers are inside the matrix, fibers inside the matrix. So different layer, different angle we can do it. So even multiple layers can be put in multiple, sometimes 0 degrees, sometimes 45 degrees, sometimes 90 degrees. So depending upon the force, we tailor the lamina. This is a plate subjected to in-plane load, in-plane harmonic load. Harmonic load means in-plane harmonic load varying with time, like wind load. So roof is there and wind is blowing. Cyclone is coming. So now it is 10 kilometer per hour, then 20 kilometer per hour, then 100 kilometer per hour. So it's a load changing with time. So that's harmonic loading. So this is a cell under harmonic loading. In fact, this is the basic equation of the dynamics, which is explained with the help of Hamilton's principle. T is the kinetic energy. This is the strain energy. This is the work done by non-conservative forces. So normal problem we do conservative forces. Non-conservative forces means you at least you understand the significance of this, where the directions of forces vary with time. Torpedo, missiles, interceptors. You can see a lot of applications nowadays in the wars. So interceptors are, everybody has kept interceptors for the enemy attack, to counter the enemy attack. When Hamilton's principle are applied to a discrete systems, it can be expressed in a more convenient form using Lagrange equation. So this is the Lagrange equation for mostly using for finite element analysis. We do that, and this is the basic equation of the differential equation of motion. So M is the mass matrix, this is the displacement, this is the damping matrix, this is the stiffness matrix, this is the force varying with time. If damping is very small, ignoring damping, we will get into K minus MQ is equal to 0, which is free vibration. K minus PCR kg, geometric stiffness matrix, is static stability, and this is called a dynamic stability, which is applicable to harmonic loading. Harmonic loading, as I have told you, this is applicable to harmonic. Static stability means buckling. Pre-vibration, you understand. Pre-vibration means you give a force, vibration started. As long as vibration started, you remove the force, so it is pre-vibration. If force is continuously applied, it is force vibration. So in fact, this is a dynamic stability means continuous in plane load. So any element can be used. This is one of the element we used, 8-noded conventional 8-noded element we have used it. This is the layer wise. This way the composite layers have been done. Layering has been done. One, it can be 4 layer, it can be 8 layer, it can be 6 layer. So it can be linear, non-linear. This is the strain displacement matrix. This is the constitutive relation. You can see it here. The constitutive relation contains Young's modulus in one direction. So if it is a isotropic material, it will be E by 1 minus nu square. So this will be E by 1 minus nu square. If it is a composite, so both are different. So Q12 and 21 both are different. This is Q22 E by 1 minus nu square. If it is isotropic, both are, these two are same. E is same. So using this, the constitutive relation is defined. This is in plane terms, D is the bending terms, this is a coupling terms, B are the coupling terms, and this is shear terms. So these are being used. So this is the corresponding strains. In plane, bending, shear. In plane, bending, shear. In plane, bending, shear. So these are the corresponding terms. These are the stiffness matrix. This is the mass matrix. This is the geometric stiffness matrix of the system. This is how the flow chart to develop the program. We have developed a program in MATLAB for various kinds of problems we are talking about. The formulation can handle geometry, including delamination, material, general distribution of temperature, moisture. Multi-point constant algorithm is incorporated in finite element for delamination. Then comes experimental program. Experimental program, as you can see, glass fiber, carbon fiber, epoxy, hardener, polyvinyl alcohol. So these are the materials being used. This is the materials, fiber. These are used for, these steps are used for create artificial delamination. So this is the casting of composite plates. This is used for delamination different size, delamination of different size. In between layers, we create delamination. This is the plates with cutout. Some student has worked in composite plates with cutout. This is actually stiffened composite plates. In aircraft or bigger structures, stiffened plates are being normally used, and we have done it in our laboratory also and tested for. This is with carbon nanotube. So we add carbon nanotube CNT powder in the matrix itself. So with some process, these are the small equipments are being used, not very costly, small equipments. So using steering or sonication, all those things have been done, and this is being added to matrix and then with fiber. So that way it is becomes nano composites. So everything we have done it in a laboratory. So this is the tensile testing. This is the instron, which for tensile test of composite specimens. This is the failure pattern. This is the modal testing, the vibration measurement system. So the structure beam or plate or cell is made to vibrate with striking the impact hammer. This is the impact hammer. Then this is received by the so the signal is received through the accelerometer to the data acquisition system, and data acquisition system is connected with the laptop in which the pulse software is there. So it converts the time domain signal to frequency domain software, and we saw the coherence. We saw the FFT. FFT software is here. So if we saw the FRF, frequency response function, and coherence within this laptop. So this is used to humidity chamber, temperature bath. This is the display comes from the laptop during vibration measurement. This is the typical vibration measurements. So this is called FRF. So these are the peaks at the corresponding frequency. So with that also we get coherence. Coherence gives you level of accuracy of measurement of the system. So there are different boundary conditions have been created using this frame. Fabrication, we have done the fabrication. This is how the accelerometer is attached and the impact hammer is hitting. So it will vibrate, and then the accelerometer is connected to data acquisition system. This is cell, curved panels, fabrication procedure, casting of fiber metal laminate. You can see bottom aluminum and fiber. This is the CNT, carbon nanotube. This is graphene sheet. This is single walled nanotube. This is single walled carbon nanotube. This is multi walled carbon nanotube. We have used multi wall nanotube. This is the CNT reinforced nano composites. Then some results. For any results, for free vibration, we need to do the convergence. Convergence study is required to decide the mesh size. For any finite element, whether you write a program or you use any software like Abacus, ANSYS or Alger, so you need to have the convergence study with different mesh size. Then you decide the mesh. Wherever it gets converged, no change in the values, then you results converge, then you can go with that mesh. There is no need of going further. So then comparison with previous studies. So the results are compared with some previous studies with different authors. Then the own results. This is the variation of natural frequency with different number of layers. Naturally, it will go on increasing. This is different modes, and this is different layers. So as you go on increasing means naturally if you increase the number of layers, it becomes more stiffer and the frequency will increase. So this is the A by B ratio. A by B ratio means aspect ratio. It's called aspect ratio. Experimental and finite element both matching to each other. As you can see, like isotropic also. So A by B 0.5, then it is the least at 1, then go on increasing. So this is for different boundary conditions, simply supported, clamped, and in between. Effect of temperature. Effect of temperature, the frequency reduces. Effect of temperature, the frequency reduces. Temperature, moisture, frequency reduces. Different boundary condition given in tabular form. Effect of delamination. If you create delamination means the frequency reduces. How much it reduces? How much is the effect with the first frequency, second frequency? Different boundary condition has been shown in this table. This is with this carbon plates, black color carbon fiber plates. This is the effect of repeated application of temperature. If you go on increasing we repeat the rolling, heating and cooling, the stiffness reduces, and after some time it remains the same. Delaminated composite plates, spherical cell, elliptic paraboloid cell. Spherical means both sides curvature is there. Elliptic paraboloid means negative curvature, one side positive, one side negative curvature is there. This is natural frequency of laminated composite plate. This is cell. RY, some curvature has been given. This is the curvature is still further increased. This is the mode shapes. Mode shapes gives us the first mode, second mode, third mode, fourth mode. Different mode shapes are there. So it gives you an idea of how the bend really vibrates, how a plate or cell really vibrates when you just give a force. Sometimes it is of this shape, sometimes it is of this shape, sometimes this shape, sometimes this shape. So if you plot it, you can see the different modes. More or less this is the first mode. More or less the bend form is the first mode. Others are, this is 1 1 1 2 2 1 2 2. This is higher temperature. Then static stability problems, buckling. So for buckling, there one more matrix is required, geometric stiffness matrix. Like this is for vibration, this is for buckling. This is the G matrix, KG matrix. So we tested the buckling. We tested on the same instron, UTM by instron. So buckling setup, we have a setup for testing. This is the fatigue testing machine. Even this is another machine, but this is a fatigue testing machine. So it can do static, means buckling test it can do, tensile test it can do, and fatigue test also it can do. Other machines are static test only do, but this tensile testing can do, but this machine can do also fatigue testing. The software is different. 3 softwares are there in the machine. This is in our lab. Fatigue failure. This in fact I have done it once, test by buckling test by dynamic approach. Buckling test by dynamic approach means, so we first find out the natural frequency of the system, then we give load from the both sides and try to measure the frequency rather than buckling load. The load at which the frequency of the system is 0 is called the buckling load. That's called buckling test by dynamic approach. This system is there in the structural laboratory. This was fabricated with the help of a project, DST project. Then parametric instability test, which is the dynamic stability test. This is the arrangement. So we give both static load and dynamic load at a time and see the behavior. This is the buckling load with different number of layers. This is what is called buckling study by dynamic approach. You can see this is the natural frequency of the structure. Then we give go on giving load, it comes to this one or this one or this one. Then we extrapolate the point at which frequency is 0, that is that load is called the buckling load by dynamic approach. This is in fact recently some of still working. She has not submitted. This is buckling load for with nano composite CNT percentage for different percentage of CNT 0.1, 0.2, 0.3, 0.4, 0.5. So the buckling load increases for certain 0.3% of CNT, then decreases. Decreases means actually the possible regions is probably the mixing is not proper. So it becomes difficult when you go on increasing the percentage of CNT. This is the wedge-shaped dynamic instability curves. This is the zones of instability. This is the zones of stability. This is done based on the dynamic stability formulation, harmonic loading for different layers, 8 layer, 12 layer, 16 layer. This is for 16 layer. This is for 12 layer. This is for 8 layer. So as you can see, the excitation frequency is higher for 16 layer than the 8 layer. This is dynamic, the instability regions have been plotted for square and rectangular curves for different aspect ratio 1.5 to This is for different boundary condition. This is for clamped. This is for simply supported. Clamped will have more excitation frequency than the simply supported one. Then orientation. Again, number of layer. This is the fatigue testing. We have done the fatigue testing. You can SN cycle, SN curve for 8-layer symmetric cross-ply laminated flat panel at 350 Kelvin with 0.5 Hz load frequency. So our machine having a capacity of, it can take up to 5 Hz. So we are given some dynamic load and static load. So both have been given and the fatigue behavior has been studied. So the conclusion, the finite element formulation to study the vibration, buckling, dynamic stability of industry-driven woven fiber laminated composite plates and cells. Result, present the FEM formula shows good agreement with the existing literature. So from the above studies, it can be concluded that vibration behavior of the laminated plates is greatly influenced by the geometry, material, ply layoff, temperature, moisture, delamination, curvature, orientation, and type of materials. So these are parametric conclusions. What is the effect of different parameters? So the designer has to be cautious while dealing with structures subjected to dynamic loading. This can be used for tailoring. So depending upon the load coming onto it, you can change your direction of the fibers. You can change with your material. You can change with, if it is subjected to fatigue loading, you can give it tailoring, do the tailoring itself. So for different kinds of loading, if it is tensile loading, so the orientation is one. If it is bending, the orientation is another one. If it is subject, so vibration results can be used as design aids for the dynamic design of composite structures. The modal test results can be used as a tool for structural health monitoring of structures, including location of damage in composites. These are some of the references, acknowledgements. With this, I finish my presentation, but you are free to ask questions. Any doubt, anything you can ask me.
Sir, I have a question, sir.
Please tell.
You have done a test where you are applying the action load.
Yes.
And you are measuring the frequency.
Yes.
For dynamic.
That is a buckling load by dynamic. Buckling load by dynamic approach.
Yes, sir. What is there any advantage of doing that? Doing such test?
Means actually advantage means either you have to make a buckling load arrangement or you can cross check. It has a advantage. Yes. When you do finite element analysis, before I do the experiment, when I have done it, when we doing purely finite element analysis, somewhere actually I faced numerical instability, no result coming. No result coming. So it is locked. Somehow it is locked. Numerical instability occurs. In that case, the buckling load through dynamic approach we have found out is the only solution through numerical methods. Experimental is one side, and numerically, in some situations there is numerical instability occurs where you need to go through that formulation and get the buckling load through dynamic approach. I have shown a diagram. Buckling load through dynamic approach.
It is coming down. Like this.
Coming down, then
interpolation.
Yes.
Extrapolate.
That one. Somewhere numerical instability occurs. I have faced also multiple times. In that case, buckling load cannot be obtained directly. K minus lambda kg is equal to 0. If you cannot get it, then the other way is this one, because this buckling load by dynamic approach never fails, because you are measuring frequency. Okay, understood?
Yes. Yes, sir. I'm working currently. Yeah, yes, sir. And little bit I'm looking to that area, so I just curious about that
Okay,
approach.
fine. Any other from the participants? Anything from the participant side?
Participants can ask questions to sir. Uh,
You can unmute yourself and ask question. Anyone? Any question? If there is no question, then we can stop here.
so yes, sir. So
Yeah, thank you, sir,
Thank you.
for the
Thank you.
informative talk. Thank you, sir.
Okay.
so thank you, sir. Let us all thank Professor Shishir Kumar Sahu sir for his presentation on application